So it turns out that to be able to look for options at constant stiffness, if you want to look at differences in shape, you can basically get to the point with the information that we have generated up to this point that going from shape A to shape B, you can make this material more viable to be effective in a certain design. We do that by a modified material index that takes into account the shape efficiency factor. So instead of e to the power half in the numerator, you have the term phi, in this case phi sub e times e, the whole to the power half divided by rho. That is the new material index. So if you divide both the numerator and denominator by this term phi, you basically have e divided by phi, the whole to the power half, and rho divided by phi. So you can use the same plot of E versus rho and divide terms in the y-axis and x-axis by this term phi. So for instance, you could take aluminum, and if you go to this new form of aluminum where you divide the modulus by 44 and you divide the density by 44 as well, you will get a new material that was in this region that is not represented by any material in the original E versus rho plot. And this new material would have an effective modulus of E over phi, where phi is a shape efficiency factor, and an effective density of rho over phi. And so you're basically filling up all these hollow spaces in the bubble chart in a material landscape. So basically increasing the ability to use known materials by creating new shapes to make them more effective in a design, in this particular case, stiffness limited design. How do we derive these shape indices will be the subject of the next class. Let us go from this stiffness limited designs to strength limited designs. In this case, we again look at the reference cross section as this square cross section tie rod. In this case, the moment z is a raised to 1.5 divided by 6, where a is, for a square cross section, b square, where b is the length of the side. If we keep the area constant and move it to new shapes that can be considered for a particular structural design, we basically come to the case where z is I divided by y max. And so the shape factor for a strength limited design in the bending form of loading can be defined as the ratio between the bending strengths for the new shape to the reference to the original shape, which is a square cross section. So in this particular case, it is the failure strength for the material times z divided by the failure strength for the material divided by the reference moment. If you introduce the term for z naught from this equation over here, you basically get the shape efficiency factor for a strength limited design, so under bending conditions, to be 6 times z divided by a raised to 1.5 as a power. How do we use this information? Let's again revisit those 5 geometries that we considered earlier, right? The rectangular geometry, cross-section of sides B and H. We know what the area is. The moment Z now is BH squared divided by 4. And if we substitute for Z and substitute for A in this equation, in the numerator and denominator respectively, we will be able to get a shape efficiency factor for the loading condition for a strength limited design under bending. So when B equals to H, you would come to a situation where the shape efficiency factor would be 1. But for when B is not equal to H, it will be H divided by B to the power 0.5. That's what will emerge when you substitute Z and A into this equation over here. So that's the shape efficiency factor for a strength limited design. What about a circular cross section? You have a radius r, we know the area is pi r square, and the moment Z from table 9.2 can be referenced as pi by 3 times r raised to 3. So if we now want to calculate the shape efficiency factor for the circular cross section, we substitute moment Z in the numerator, area A in the denominator, give it a try, and see if you come up with this answer, right, from this equation. So again, just like we had seen in the case of the stiffness limited design, where this was a constant 3 divided by pi, which is about 0.955. You have another constant, in this case 0.85. If instead you take a tubular cross section of outer radius r0 and inner radius ri, thickness t, and the thickness being very small relative to the radii, you can approximate the area we have seen as 2 pi r times t. The moment Z from table 9.2 is, as an approximation, pi r square times t, when r is very much bigger than t. Again, substitute Z into the numerator, area into this term in the denominator, and you can get the shape efficiency factor for the tubular cross section. If you give it a try, then basically you will have a term of 3 divided by square root of 2 pi times square root of r divided by t. For a rectangular box cross section, so it's a hollow rectangle, again t is small, and so we said that the area is 2t times h plus b, when t is very small compared to h and b, as one approximation. Moment Z in this case is given by bht times 1 plus h over 2b. Substitute Z and A. What do you get? What you get is this term over here that depends just on h, t, and b. And then you can, using this shape efficiency factor for a strength limited design, you can deduce in a similar manner what happens when B is the same as H for a square cross-section geometry. This term over here drops off to square root of H over T. 4 in the numerator, right? 2 times root 2 in the denominator times root 2. So you're reduced to this term over here. You would imagine then, based on how we saw for the stiffness limited design earlier, that for the strength limited design, again, the terms would be the same. For Z, A, and the shape efficiency factor. So we've taken some common cross sections so far, and for a stiffness limited design and strength limited design, derived shape efficiency factors. We had earlier seen how that can be used in an E versus rho plot for a stiffness limited design. So we have also come across